What I want to do today is to discuss about technology node and MOSFET scaling. Now, what are technology node? So, a particular technology node is referring to the production of chips with the transistor having a minimum feature size of a particular value. Okay. Say for example 1 micrometer. So that we call as 1 micrometer technology node. So to get an idea of this, you can go to one subsidiary of Wikipedia, which is called WikiChip. Okay, if you just Google technology node, you will get into this site. Now, if you look at on the right side, okay, so there is a definition of technology node here. So technology node or process node, process technology node, these are different ways you can call it. Let me just maximize little more. Hope you can see this. It refers to the specific semiconductor manufacturing process and its design rule. Okay, so this is very much the whatever process that you are going to use in manufacturing is going to be decided by the smallest feature size that you require. Okay, and the features are going to be transferred into the chip through a process called lithography. So the most critical process is lithography. We will look at what is lithography, how it is done in a later class. But that is the process which defines or that helps us to achieve very the smallest feature size in the chip manufacturing. Okay, so we can transfer the dimension, the features, dimensional features into the chip while fabrication using this process. So lithography is basically a pattern transfer process step. There are various process steps like diffusion, ion implantation, okay, growth of the layer, deposition of the layer, etc. But to transfer the pattern, we use what is called as lithography. Now, on the right side, if you look at, you see various technology node. Okay, so if you go to the bottom of it, you will see 50 micrometer. So, which is a very old technology node. If you go to that page, okay, so you can get an idea what kind of transistors and chips were manufactured using 50 micrometer lithography process. Okay, so the channel length of the MOSFET is of the order of 50 micrometer. That's what we mean. Okay, so you can also, usually this is lambda length. So lambda 2 lambda is basically the length, so it will be 100 micrometer will be the channel length. Okay, so which companies were manufacturing, some details you can get here. Okay, so there are not much. So here it is talking about a company called Fairchild, which was a prominent company in those days. Now if you go to other technology nodes, say for example 1 micrometer. So this was in the 1990s. Okay, so or 1980s, 1990. So it started in 1980s, 1 micrometer lithography process, and then it was replaced by the following technology node in the 1990s. So this was basically used for making microprocessors. What were the companies who were fabricating this chip in those days. Intel was the main player. You can see here 1984 they came with the first production, okay, and then they have changed the process slightly bit and came up with a more refined process 87, 91, etc. Okay, HP also played, and National Semiconductors. Okay, so these were CMOS, and this is BiCMOS. BiCMOS referred to bipolar junction transistor combined with the CMOS. So that's a technology. We can look at that also. And you can see 80386 processors, so which are like after 8086 they have 80286, 386, 486, etc. And after that came the Pentium processors. So these 386, 486 processors were made in 1 micrometer technology. Okay, so let's move upward. Like then one major technology was 180 nanometer. So that was as you can see in 2001. Okay, it started in 2000. Okay, so it's the turn of the century, and the players that are involved here. So now there are more companies that are coming into the domain. So TSMC also came in 2000. Then Intel it was already there. Intel is the one who started with IC manufacturing, and I think the CEO of Intel, Gordon Moore, also had a law called Moore's law credited to him, which basically talks about the way in which the technology is going to be driven with respect to the timeline. He's predicted something like every 1.5 year period, the package density, the transistor density in the chip will double every 1.5 to 2 years. So that is almost that trend you can see even till today. So you can see all the companies like Intel, Fujitsu, TSMC, Motorola, IBM, Samsung, Texas Instruments, AMD. So these are the companies you can see here. So this is 180 nanometer. Different companies may have different years when they start this production. You can see TSMC started in 2000. Intel has already started in 1999. Okay, and Samsung also like 2001. So Intel was the first to get into it. Then came TSMC. Then came Samsung. So now what is remaining today is Intel, TSMC, and Samsung. These are the three major players. All others are operating still at a lower technology node. Okay, so let's move on. So from 180 nanometer, so let's go to 32 nanometer. So 32 nanometer is important because the current CMOS that we have been studying, so CMOS based transistor being used to manufacture, so that was having not much problem till 32 nanometer following those approaches. But the moment we crossed 32 nanometer node, it became a problem to continue that device, to scale down that device. So that scaling is what we are going to look at today. So 40 nanometer. Okay, so this was which year? 2010. Okay, so 2010 is the year in which commercial production started. So testing will happen maybe 1 or 2 years before, and they will have some time period for they will produce, but not in a mass scale, just to see what is going to be the yield rate, whether it is working without error, etc. So they will undertake massive testing during that time. So now you see, when it comes to 32 nanometer, Intel 2009 TSMC year is not given. Common Platform Alliance, I don't know what it is. So maybe a group of companies might have come together. So then Toshiba, okay, so few more companies. And what are the chips that are manufactured? See, you can see all this i3, i5, i7, all of this were made using 32 nanometer technology. Okay, so now if you look at the usual trend of the way in which technology node is going, you can see this pattern. Okay, so for example, this is our 1 micrometer, and if you multiply with 0.7, okay, 0.7 is a very magic number kind of thing. Why it is? It's because 0.7 is 1 by root 2. That's basically the reason. To be more exact, it is 0.707. 1 by root 2 if you take 0.707. So the length scale of the dimension of various features in the transistor, like width, length, oxide thickness, depletion width, all these lengths are going to be scaled down by a factor of root 2. Okay, so root 2, it gets divided by root 2 or multiplied by 0.7. So these are two different ways you can look at it. And so from 1 micrometer, if you divide it by root 2, that is 1.4, then you will reach say 700 nanometer. Again, you multiply it with 0.7 or divide by root 2, you reach 500 nanometer. And roughly, if you look at the history of the technology node, roughly it takes 2 to 2.5 years to go from one node to the next node. That is multiplication by a factor. So if you are at 32 nanometer, you are supposed to go to 22 nanometer. Okay, so that is how you should be planning ahead to venture into the new technology node. But if you look at what actually happened after 32 nanometer is that instead of going directly to 22 nanometer, it went into 28 nanometer. Okay, and there was reason, because 22 nanometer the MOSFET was not working. Okay, so they were doing rigorous test. There were a lot of short channel effects which were coming into the picture, which they are not able to control or manage. So therefore, going directly to 22 nanometer was not possible with the conventional MOSFET structure. So then they were thinking about changing the device itself. So we need basically a transistor which is basically a controlled switch. Okay, gate voltage controls the current from drain to source. So that is what we want. So MOSFET was very successful in doing that, but as the dimensions began to get reduced, that became more and more difficult. So 32 to 22 nanometer, that became like almost impossible. So there was some time they were making effort, but then ultimately they succeeded with the 28 nanometer. They couldn't succeed with the 22 nanometer. So this was the last node where conventional MOSFET was made use. So the scaling of MOSFET, when we talk about, say, from 1 micrometer or 50 micrometer, it goes by multiplying a factor of 0.707. Each 0.707 multiplication takes around 2.5 years, and after many nodes, it has reached 32, and then it was not possible to go into 22 nanometer. So then what happened? So this is the last MOSFET node. 28 was then made. So TSMC, so by that time TSMC became like more prominent manufacturing foundry. Okay, they have grown so much. Then okay, so you can see Apple's chips were manufactured, A9, A10. These are the chips in the your iPhones. Okay, so that were made in 28. But you can see that Intel did not Intel is also there. Intel directly did not fabricate it. Intel's design was fabricated using TSMC. So Intel did not have a node at 28 nanometer. So you can see here, there is no mention of Intel here. Okay, so that's the time where TSMC is becoming more prominent. Okay, so what Intel was then doing was they were focusing on 22 nanometer instead of going into 28. They directly went into 22 nanometer, and in 22 nanometer process, again as I told you earlier, lithographic process is the critical step involved in the entire manufacturing, and that takes half of the cost roughly for manufacturing, that making that single process, because that is repeatedly done. If you look at the manufacturing process, lithography is done like 30 times, 40 times, etc. For every pattern that has to be made in the chip, you have to transfer the pattern from the computer design, the layout design, into the chip. So that is the most critical step. So 22 nanometer, now if you read here, you have a new device entering. Okay, so far it was conventional MOSFET. So you can see that 22 nanometer simply is a commercial name. Okay, just like we used to talk about technology node in terms of the minimum feature size, lambda, where L is the length which is equal to 2 lambda, but that definition no longer holds. Okay, because it is no longer the MOSFET, conventional MOSFET structure that we are going to use. Instead, it is going to be made with what is called as FinFET. So FinFET is something like this, as you can see here. If you compare it with MOSFET has a planar structure. Okay, so here FinFET has a something like a 3D structure. Okay, so you can see that the gate is covering 3 sides, top, then left side and right side. Bottom side you don't have a gate. So and the channel is actually in between. Okay, so it is like holding the channel by wrapping the gate on 3 sides. Okay, so 3 sides is covered, and so that way you can achieve more control over the channel. The gate voltage will restrict the conductivity of the channel by changing the voltage. So that's basically the idea. So that came into existence, and lots of videos are available in YouTube. You can search about this 22 nanometer FinFET technology. Okay, Intel has released many videos about it. Okay, so then from 22 nanometer onwards, FinFET became like very prominent. Now if you look at the current microphones, mostly you will see 7 nanometer. The current microphones, mobile phones that you are holding in your hands, if you have purchased it in last 1 year, then most likely the processor inside will be having FinFET transistors, which are having a minimum feature size of 7 nanometer. Okay, so now who are the players for 7 nanometer? You can see that Intel, TSMC, Samsung. Okay, all others are not able to start manufacturing, so they still continue with say 10 nanometer or older technologies. Global Foundry also cancelled their plan to scale up to 7 nanometer. So finally it is these 3 are only in the scene. and you see the lithography, what they use is extreme UV lithography. Okay, so that's a current more recent version of lithography. And okay, so these are the design rules for making FinFET. Okay, we are not going into that. So it is also called, this 7 nanometer node is also called N7. Okay, N7 refers to 7 nanometer node. Okay, so it has come I think 2019, major from around 2018, 2019. Okay, so that's why I said most of the mobile phones that you carry will be having chip, Snapdragon, etc. Will be designing for 7 nanometer, and they will give the design to TSMC or Samsung to manufacture it. Okay, and then what is the current status? The current status, the commercial production started in 5 nanometer. Okay, so in 2020 around, yeah. So 5 nanometer was set to begin sometime around 2020. So it's already into production. Especially I think memory chips. Usually whenever a new node comes, the first chip they used to manufacture is basically the DRAM or SRAM chips. Basically the memory chips, because memory is a very highly dense chip. Okay, and similarly FPGA chips also is very highly dense chip. So usually because they have a regular structure, so regular structures are like more easier to make initially. So once they get mature, then they will take processors and other chips also. So current status is 5 nanometer, and what is in research phase is 3 nanometer. I think 3 nanometer is set to come in 2023, okay, sometime in 2023. So right now we are in 5 nanometer technology node. So again till 5 nanometer FinFET was continuing, but when it comes to 3 nanometer, again FinFET also is not possible to give result. So okay, so people are working on different things. So okay, so TSMC is trying with FinFET, but Samsung is going into something else which is called GAA, and GAA stands for gate all around. So FinFET, I told you, it is gate appearing in 3 sides of the channel to get better control, but gate all around means all the 4 sides you have gate. So that means completely it's like holding a pipe and pressing it, so through which water is flowing. So you completely cover from all the sides. So that's the status, gate all around. Yeah, here it is, gate all around FET. So that is the most recent device, which is now not yet in the production, but maybe in 1 or 2 years that will be coming in. Okay, so these are the technology nodes. So what we are going to do today is basically to discuss about the scaling of MOSFET. Okay, MOSFET has been in a conventional transistor that is used in the digital circuits from 50 micrometer to say 28 nanometer. So there is a long number of years MOSFET was still MOSFET is important. Doesn't mean that when you start production in 5 nanometer you don't use all other technology node. The foundries which are made to construct at say 28 nanometer, they continue their production, okay, at those nodes, but only certain critical chips, processor chips, they will only be produced at more higher nodes. And the cost of production also increases as you go into a newer node, more recent node. So therefore some design company is not able to bear that much cost, and therefore they continue to produce devices by using earlier nodes. Okay, And all the analog chips still did not get into FinFET. Analog chips are still with the conventional MOSFET. Only the digital chips are going into sub say 22 nanometer, 22 nanometer and lower technology node or dimension technology node. Only the digital chips are actually being manufactured. Okay, so that's just a background of technology node. So as I told you, scaling is reduction of dimension of the features of a transistor. So what are the features of transistor? So there are many features. Some are dimension. So you can classify them into two categories. One is dimensional, other is voltage, okay, which is basically electrical features. Okay, so now scaling dimensional, so dimension means length, width, then depletion width, this kind of thing. Scaling dimensional features is relatively more easier compared to scaling electrical voltage. Voltage means your VGS, or you can say VDD. Okay? VDD will decide your VGS and VDS, etc. And then another critical thing is VT. Okay, so VT and VTP, etc. So VT is threshold voltage. So it's very difficult to basically scale down your VT or reduce VT. If you can reduce VT, you can reduce VDD, but reducing VT is very difficult because it depends upon various things which we earlier discussed in the derivation of VT, flat band voltage, impurities. So it so much depends on the material properties, etc. So since VT cannot be changed, VD also cannot be changed. So there is a limitation. So people are trying so many different ways how VT can be changed. So, but it's not that easy as compared to changing the dimensional features, scaling down the dimensions. So we are, whenever we talk about reduction of dimension, so let's call L dash XD dash say corresponds to new node, and L, W, XD, etc. Correspond to old technology. Okay, so when you go from one node to the next, what happens? Basically, your L dash is scaled. Okay, so L dash is equal to what? L divided by S. W dash is equal to W divided by S. X dimension is equal to this is the depletion width. That means whenever we have a PN junction, there is a depletion region width. So we have earlier looked at what is going to be that width, etc. So that will be X dash XD divided by S. Okay. So where S is basically root 2. Okay. So where I am talking about two successive nodes. Okay. So the new node is basically the successive node of the earlier node. So S, which is 1.42, etc. So it is a parameter greater than 1. Okay, and why the root 2 became more important? That's because if you look at area, so A dash is what? The area of the gate, which basically give an estimate of how much big is the transistor. So that will depend upon this A dash. So A dash is basically L dash into W dash. So which is what? Which is basically L by S into W by S, which is equal to L into W by S square, which is what? L into W by So L into W, I can write it as A, earlier area, divided by S square is what? 2. So area is halved. Okay. So if area become halved, then the number of transistors that you can make in a given wafer or a chip area is doubled. So that's basically the idea. We are trying to double it when you go from one technology to the next technology node. So therefore this number S is made as root 2. Okay, so now as I told you, the second group of parameter which is more difficult to be scaled down, and that is basically the voltage parameters. Okay, so let's look at different so there are different types of scaling. So let's look at types of scaling. So I would like to classify them as generalized scaling, and number 2 is constant field scaling, and number 3 is constant voltage scaling. So in generalized scaling, what we will do is that we will have two parameters where alpha and beta we will call them, and in constant field scaling there is only one parameter, so that is basically S. Everything is scaled by same parameter, or you can say that alpha is equal to beta is equal to, so it's a special case, generalized scaling special case. If you take alpha is equal to beta is equal to S, so that is called constant field scaling. And in constant voltage, what we do is alpha is equal to S, but beta is not scaled. Okay, beta is 1. So these are, so if you know the generalized scaling, then it is very easy to see constant field. So constant field scaling is also called as full scale. Full scale, because everything is getting scaled equally, so it's called the full scaling. And this is partial scaling. Only if some of the parameters are getting scaled. Okay, so now let's look at what happens with the generalized scaling. Okay, so to see that, so let's take all the different parameters. So what we say is the dimensional parameters are getting scaled by a factor S. Okay, so we are going to look at the number 1, that is generalized scaling. Okay. So in generalized scaling, as I told earlier, L dash become L by alpha, and then W dash become W by W by alpha, that is also dimension, and then T ox, which is basically oxide thickness, so that is also, sorry, let's call it as alpha. And the other important VDD, so VDD dash. Okay, so earlier it used to be 5 volt, and then it has scaled down, then it became 3.3, then later it became 1.1, then now it is something like 0.8, 0.7, like that. Okay, so that is VDD by beta. So if we take these and also VT, VT dash is equal to VT by beta. So if we take these, what will be the consequence? So basically, whenever we talk about scaling, we need to see what is going to be the consequence of taking the parameter value like this. How will you compare various derived parameters like current? What will be the change in current? What will be the change in area, etc. So the first thing we will look at is basically the current. So drive current, effect of scaling on drive current. So when we calculate drive current, we will assume a saturation region of operation. So the new current, saturation current, ID sat is equal to, so we have mu and Cox dash, it will come, and then W dash by L dash. Okay, so everything is now with dash, and VDD, VGS is basically VDD dash minus VT dash, the whole square. Now all you need to do is basically express mu n is mobility, so that is a material parameter. Whether you have a bigger transistor or a smaller transistor, that does not get affected. So what about Cox? So let us look Cox. Cox dash is basically epsilon ox divided by Tox dash. So epsilon ox is also material property, that will not get affected. So but Tox is what? Tox dash is basically Tox divided by alpha, so like this. So which means that alpha into Cox. So you can now substitute mu. So Cox dash is basically alpha into Cox. So that is number one. And the next one is W by L. Both are scaled by same factor, and we are taking ratio, so it doesn't change. So that is W by L itself. And then next is VDD dash. So that will be VDD by beta minus VT by beta, the whole square. So ultimately, if you look at if you collect the beta outside, so it will become beta square, and there is an alpha here, so alpha by beta square into, and the rest of the term is basically mu Cox W by L and VDD minus VT whole square, which is basically the earlier current. Okay, so you can write it as simply alpha by beta square, alpha by beta square into ID sat. Okay, so that is, so ID, the new drive current is alpha by beta square into earlier. Okay, so that is basically the factor by which the driving current will get scaled. Now let's look at another important derived parameter of the transistor. So number 2, or say B. So here we can talk about intrinsic gate delay. Now how do you estimate gate delay? It's basically the capacitor, gate capacitance getting charged with the drive current. So earlier we calculated the drive current, so that drive current will make the capacitor to charge, and the amount of charge that it will finally get charged to is basically the gate capacitance value multiply. So the delay, so tau, an estimate is basically q, that is the charge, q final divided by id. So we are just making an approximation. The current also changes because the transistor will operate for some time in saturation, then it will go to linear, etc. during the process of charging, but we are neglecting all those second order effects. We are just getting a estimate of what is the effect of scaling. Okay, so if you want the new timing, you have to use okay, so for new technology node, what is going to be the charge to which it has to be charged, the capacitor has to be charged, and what is the current. So charge by current will give you the time it takes to charge. So we are in a way assuming constant current, but again that is also an approximation, but this will give us an estimate. Okay, so now what is charge? Charge is basically the Cg dash, the gate capacitance, multiplying the voltage to which it gets charged. So that final voltage is going to be VDD dash. Okay, so Q is equal to CV, that's what we are using, and this divided by ID sat. So now we just need to substitute ID sat new. We have already found out it was basically S by it was basically alpha by beta square, alpha by beta square ID sat, right? That's what we just got it, alpha by beta square ID sat. So that's the denominator. What about the numerator? So how is the gate capacitance getting changed? Now what is gate capacitance? So Cg dash is what? Cg dash, Cox is gate capacitance per unit area, and you just need to multiply it with L dash into W dash. Okay, so Cox, I think we have found it out. Cox dash is basically alpha Cox. So alpha Cox, alpha Cox, and then L into W, so that will give you alpha square into LW. So it will be alpha cube Cox into LW, so that is our old Cg. So we can now write C gate let me just see, did I make a mistake? Cox is so Tox is scaled by alpha, so Tox by alpha, so it should be, the capacitance is increasing. Okay, if you reduce, yeah, it is increasing, and then it is increasing. What about, oh, okay, I made a mistake. So the mistake is L dash is going to decrease, that's what we said, right? Scaling means length and width are going to be divided by S. Okay, so that's what, it should not be alpha cube. So this is basically L into W, so L by alpha, W by alpha. Okay, so one of this alpha will cancel, and then you have Cox LW by alpha, which is Cg by alpha. So you can substitute that Cg by alpha. Then what about VDD dash? VDD dash, we already told that it is going to be scaled by a different factor, that is VDD by beta. Okay, so now if you combine everything, so you can write Cg VDD by ID sat, and you take all other term, there is 1 by alpha, there is 1 by beta, and alpha by beta square, if you take the inverse and multiply beta square by alpha, so that will cancel 1, so it is beta divided by alpha square. Okay, so this is going to be the factor by which the transient delay, that is the time it takes to charge, this is basically an estimate of propagation delay. Okay, so next is number C, power dissipated per device. That means how much power is dissipated per device. Okay, so which we have calculated earlier. So an estimate of power dissipated per area. There are different types of power. Right now we are not bothered about all the different types of power, etc. So we are going to look at so here what we are going to do is the peak power. So peak power for the new node, we will define it like this, ID sat. So this is not particularly the dynamic power or static power or short circuit power. There are three kinds of power which we looked at earlier, but this is just a an estimate which capture everything in just one quantity, so which is basically the saturation current multiplying with VDD. Okay, so this in some form or the other way it will be reflected in the other power, like the dynamic power, like charging the load capacitor or parasitic capacitor through the PMOS. If VDD is different, that will be different, and then the ID sat, so it will give an estimate. Similarly, short circuit power also depend upon VDD and the short circuit current. Okay, so we call it as the peak power. Okay, so this is the maximum power that can be dissipated in the MOSFET. We are not categorizing it into a particular category. So just multiplication of saturation current with the voltage. Voltage into current is power. So that so we have already found out ID sat. It was what? It was alpha by beta square. So alpha by beta square into ID sat. So our main interest in these evaluations are basically to compare two successive nodes. So with respect to the previous node, how things are going to be in the new node, whether it is increasing or decreasing, etc. So that's our main aim. So then VDD dash is going to be VDD by beta. Okay. So that is going to give us the alpha by beta cube into earlier peak power. Okay, so this is the way. So you can see that alpha is something like 1.4 and beta may not be 1.4, it may be something like 1.2, something like that, but if you take the square of it, definitely it is going to be greater than alpha. So we get the reduction of power, which is very important. Power consumed when we are packing double the number of transistors in the same chip. If the power is not reducing, it will heat up tremendously, and to capture the amount of heating, we need to look not only just the power dissipated per device, but also the power dissipated per unit area. Power dissipated per, this is more important. So ultimately the scaling is to make the device in with the lesser power consumption and faster operation and lower cost. So these are the three main aim when we go from one technology node to the other. Okay, so what is this? This is per unit area. Earlier we per unit device, per one device. So now we need to multiply it with the number of device in one unit area. So an estimate of area consumed by one transistor is basically product of W and L. Okay, so if W by or W into L is this is basically area of one transistor. So therefore number of transistors per unit area is given by 1 by W dash L dash. Okay, so W dash L dash is basically area of required by one transistor. So number of transistor per unit area will be inverse of that. Okay, so it's just like frequency and time period. Alright, so we know the power consumed by one device, so you just need to multiply it with 1 by WL dash. So power, peak power dash into 1 by WL. So that is, so we have the formula for peak power, which is alpha by beta q into peak power, and then W dash is basically W by alpha and L dash is basically L by alpha. So that is alpha by beta cube 1 by alpha square, so that will be alpha square into P power peak divided by WL. So this is basically the earlier power per unit area, and therefore the new power per unit area is basically alpha by beta whole cube. So if we have to keep the heating per unit area same as corresponding to the previous node, then it's very important to have full scaling, because in full scaling alpha is equal to beta. So this is a one of the menace of the scaling is, if you don't do full scaling, you are going to produce more heat per unit area. Okay, so therefore to produce or to keep the heat production, or heat dissipation in the chip same same as in the earlier node, alpha should be equal to beta. That is the only way. Otherwise, and as I told you, it is difficult to achieve alpha equal to beta, and therefore what is going to happen is that per unit area more heat will be generated in the newer chip. This is per unit area. Per transistor it is not correct. Per transistor, if you look at it is reducing, but because we are packing more transistor in unit area, so per unit area the heat is going to rise. So that's what happens with the constant voltage scaling. So if you do the full scaling, you can keep that. So now you can compare. We have derived for generalized scaling, and if you put alpha is equal to beta is equal to S, then you will get constant field scaling. That is the most desirable scaling, the second one. Okay, so that's the most desirable. This is the most desirable, and this is not very good. And this is like somewhere an optimization, because we are helpless, we are not able to scale down VT, and therefore we try to reach somewhere in between very good and very bad. Okay, so that is, I am not specially deriving the other two. You can just substitute S alpha equal to beta equal to S, you get constant field scaling, and you can make a table. So for each of the scaling, how different things are getting modified. Okay, so only thing you need to do is alpha equal to beta equal to S for constant field scaling, and you put beta equal to 1 and alpha equal to S, that is constant voltage scaling. And why it is called constant field scaling? Because field is what? Field is basically voltage divided by distance. So if voltage is not scaled and distance is scaled, then the electric field is going to go up, which is not good. But if both voltage and, so electric field is basically equal to voltage by distance. So if both are scaled, then electric field will remain constant. So that's why it is called constant. So everything is scaled by same factor, both like by alpha. So they will cancel each other, and the electric field will remain same. So this is also divided by alpha, this is also divided by alpha. So we get V by T. So the new electric field is same as the old electric field. So that is constant field. Whereas constant voltage will remain the same, and the dimension will go down, right, and then electric field is going to rise. Okay, so that's not good. Okay, one more thing I forgot to talk about, that is basically the depletion region, the doping concentration. We need to modify the doping concentration, and how to modify the doping concentration, that will depend on which type of scaling that we are doing. Now if you go back to an earlier formula, I had it here. So I had it from our earlier class. We have the depletion region width, we have calculated as root of 2 epsilon psi by QNA. Okay, we calculated. So root of 2 epsilon by 2 n epsilon psi s, I think, right? Root of 2 epsilon psi s by QNA. Yeah. So this was the depletion region width that we calculated. So in other words, the depletion region width is proportional to this is basically the potential that is dropped across. Okay, depending upon what is the potential that is applied, the depletion region width. So it could be a built-in potential between a PN junction, or this formula is general, where psi s is basically the potential across the junction. Okay, so to use it in a general form, I don't need a psi s, I will just put VA. Okay, so this is voltage across the junction, VJ, let us put it. Okay, which means that my xd square is basically 2 epsilon silicon Vj by 2 Na. Now what I want to look at is basically Na. How should I dope the semiconductor? How should I change the doping of the semiconductor in order to make the dimension scaled by alpha and voltage scaled by beta. So for example, if I take a dash, so I need to take dash here also. So let me just, should be x d dash square. So that is equal to, so these are material constant, they doesn't matter, and Vj is scaled by beta, and then I have xd scaled by alpha. Okay, so 2 epsilon psi, then Vj divided by 2 xd square. So this, sorry, I think I made a mistake in the formula. Oh, it is q n, not 2 n. Q n. Okay, so that is also, doesn't matter, it's a constant. So this multiplied by, so there is an alpha square by beta. So this is going to be the way in which, so that means Na, the new doping concentration should be alpha square by beta times the old doping concentration. So this also can be added. So there are some criteria that is imposed on the doping concentration. So that is doping concentration. Okay. So otherwise, the depletion region will become very, very big. So we need to scale down the depletion region width in order to have a proper operation of the MOSFET. So in generalized scaling, it is alpha. So if beta is equal to 1, then doping has to be increased by a factor of alpha square. But if alpha is equal to beta, you have to increase it by alpha. So definitely you have to increase the doping concentration in order to reduce the depletion width. Okay, so these are the major effect on the secondary parameters when you achieve or when you do the MOSFET scaling by going from one node technology to another node. Alright, I will stop here.